Dear students, this is Mahesh Javalkar from Marathon Polytechnic, and today I am posting my next video on analog electronic circuits, in which we are going to see the block diagram of operational amplifier. So here, today's topic will be operational amplifier, and in short, we call it as opamp. So the contents are what is an op-amp? First we will see. Then symbol of an op-amp, block diagram of an op-amp, pin diagram of op-amp 741 IC, then ideal characteristics of an op-amp and applications of op-amp. So here we'll go to see first what is an op-amp. So if you see the definition of an op-amp, an operational amplifier, that is op-amp, is an integrated circuit that can amplify weak electric signals. So you are able to amplify weak signals. So it is acting as an amplifier. Okay, now, but what does it amplify? That will come in the second line here. An operational amplifier has two input pins and one output pin. Its basic role is to amplify and output the voltage difference between the two inputs. So it is going to amplify the voltage difference between the two input. Okay, so if you see the output voltage V naught, it will be equal to the difference between the two voltages V1 minus V2. Okay, and that also amplified version with the amplified gain AB. Okay, so here we can see output voltage will be amplified version. Here amplified version will take it as AD into V1 minus V2, where V1 is the first input, V2 is the second input, AD is the differential gain of the amplifier, and V0 is the output voltage. Okay, so an op-amp is a circuit, is an integrated circuit which amplifies the difference between its two input voltage. Okay, so that is very important. It is not amplifying any input voltage, it is amplifying the difference between the two input voltage. So if you see the symbol of an op-amp, so it is shown like this. So you have two inputs. One is called as non-inverting input. So here you can see non-inverting input. This is non-inverting input. Then the other one is inverting input. Okay. So non-inverting input, we are going to put it as a plus sign here. And inverting input, we are going to put it as a minus sign here. Okay. Then these are the power supplies. So here you will be having plus VCC supply, and here you will be having minus VEE supply. Okay, and here you will be having your output with respect to ground. Okay, so this is your V out. So here you will be having V1. See, this is V1. This is V2. Okay, then the output V0 will be differential gain, that is the amplified version of V1 minus V2. Okay, so this is how the symbol of an op-amp can represent its operation. So if you go to see that symbol in detail, you can see that inside, after the inputs, that is non-inverting input and inverting input, you can see inside there are four stages. The first stage is called as input stage, which is dual input balanced output differential amplifier. Second stage is called as intermediate stage. Third is called as level shifting stage. And fourth is called as output stage. If you see the exact block diagram, only the block diagram, then you can see it like this. First, you are having the input stage. Now, input stage will be having two inputs, which were the main two inputs of op-amp. And those inputs were inverting input. This was your inverting input, which will go to the minus sign. And this was non-inverting input, which goes to the plus sign. Okay. So first it was given to an input stage. This input stage was nothing but a differential amplifier. Differential amplifier. Okay, now it was having dual input and balanced output. So here you can see output is balanced here. So here you can see your output which is balanced. Okay. Then the second stage also will be intermediate stage will also be a differential amplifier. Differential amplifier. Now here also you have dual input, but unbalanced output. Unbalanced output. Unbalanced output means only one output line you're getting here. Only one output line you're getting. Okay. Then you are having level shifting stage. That is whatever DC level was introduced in the process, that DC level should be brought to the ground level. So it is a emitter follower circuit. This is a emitter follower circuit. So all the DC what was introduced will be brought back to ground, and the output stage will be a power amplifier. This will be a power amplifier here. So that will increase the power of the output. So this is your power amplifier. Okay. Now this is how the four blocks inside the operational amplifier will work, and then lastly you'll be having the main output which comes out. Okay, which comes out here. Now this output will be equal to differential gain multiplied by difference of the two inputs. So if the two inputs are V1 and V2, so V1 minus V2, and differential gain of that or difference of that will be amplified at the output. Okay. So the four stages of the block diagram are input stage, which is a differential amplifier dual input balanced output. The intermediate stage, which is a differential amplifier dual input unbalanced output. Then level shifting stage, which is emitter follower, and then the output stage, which is a power amplifier. Then if you go to the notes of the four blocks, then you can see these notes for your reference. Opamp is basically a differential amplifier. That is, it will amplify the voltage which is differentially present between its input terminals. Okay, so it will amplify the difference between the two inputs. Then the first stage was the input stage. The input stage is a dual input balanced output differential amplifier. The two input are inverting and non-inverting input terminals. This stage provides most of the voltage gain of the op-amp and decides, this is very important, decides the value of input resistance Ri. So the first stage, that is input stage, will give you the voltage gain of the op-amp, and it also decides the value of input resistance Ri. Okay. Then the second stage is called as intermediate stage. This is usually another differential amplifier. The input stage drives the stage. This stage is a dual input, unbalanced output differential amplifier. Okay, so dual input because there are two inputs for the second stage, but there is only one output line, so it is called as unbalanced output. Then if you go to see the third block was called as level shifting stage. Due to a direct coupling used between the first two stages, the input of level shifting stage is an amplified signal with some non-zero DC level. So level shifting stage is used to bring DC level to 0 volt with respect to ground. This is a very important function. If any DC level has been introduced, it will be brought back to 0 volt with respect to ground. Okay, that is the work of the level shifting stage. Then we'll go to the fourth stage. Fourth stage is an output stage. This stage normally is a complementary output stage. Complementary means it will be having two transistors. One is PNP and other is NPN. It increases the magnitude of voltage and raises the current supplying or capability of op-amp. It also ensures that the output resistance of op-amp is low. Okay, so it will ensure that the output resistance of op-amp is low so that you can interface it with any application. Clear? So these are the four stages of the block diagram of op-amp. Then we'll go to see the pin diagram of an op-amp. So here you can see pin diagram of 741 IC. So it has 8 pins. It has 8 pins. The first pin is named as input offset. Second pin is the inverting input. This is the inverting input. This is one of the inputs out of the two. Then third one is non-inverting input. This is also one of the inputs out of the two. So this is your first input. This is your second input, say. And then at pin number 4, you have minus VCC supply, which is also called as minus VEE. Okay, this will be around minus 12. Then fifth will be your input offset. Fifth will be your input offset here. So here you are having input offset. So pin number 1 and pin number 5, you are going to connect a potentiometer, and you will see that the output voltage is 0 for no input voltage. If the input voltage is 0, the output voltage should also be 0. It should not show any offset voltage, and that offset can be adjusted by pin number 1 and 5. Okay. Pin number 6 will be the main output. Pin number 7 will be the plus VCC supply, and pin number 8 is not connected. It is freely led. Okay. So these are the 8 pins of IC741, and this is the pin diagram. 4 pins on one side and another 4 pins on another side. So it is dual inline package. Okay. So the same arrangement you can find out in two ways. One is the circular type of way T058, in which you can see op-amp pin number 1, 2, 3, 4, 5, 6, 7, 8 given in a circular fashion. And then whatever we saw the last slide, that was your dual inline package, DIP 8-pin package. Okay, so these are two ways of producing the IC. Then if you see the IC, it is like this. It can have 4 pins on one side and 4 pins on another side, and it can show you the output pin, that is pin number 6, and pin number 2 is inverting, pin number 3 is non-inverting. Okay, so this is the view of the IC, how it looks. Then if you go to see the pin description, pin number 4 and pin number 7. Okay, pin number 4 and pin number 7 are the voltage supplies. That is the power supply. So pin number 7 is the positive voltage supply terminal, and pin number 4 is the negative voltage supply terminal. The 741 IC draws in power for its operation from these pins. The voltage between these two pins can be anywhere between 5 volt to 18 volt. So we usually use 12 volts. Okay. Then we'll go to pin number 6. Pin number 6 is the main output pin. This is the output pin of IC741. The voltage at this pin depends on the signals at the input pins and the feedback mechanism used. If the output is set to be high, it means that the voltage at the output is equal to positive supply voltage. Similarly, if the output is set to be low, it means that the voltage at the output is equal to negative supply voltage. So this is your pin number 6, which gives you the main output. Then you have pin number 2 and 3, which are the inputs for the IC. Pin number 2 is called as inverting input, minus. Pin number 3 is called as non-inverting input, plus. If the voltage at pin number 2 is greater than pin number 3, that is the voltage at inverting is higher, then the output will stay always low. Similarly, if the voltage at pin number 3 is greater than pin number 2, that is voltage at non-inverting is high, then the output goes high. Okay. Then we'll go to pin number 1 and pin number 5, which are called as offset null. Because of high gain provided by 741 op-amp, even a slight difference in voltages at the inverting and non-inverting inputs will cause, due to irregularities in manufacturing process or external disturbances, can influence the output. To nullify this effect, to make this effect zero, an offset voltage can be applied at pin number 1 and pin number 5, and is usually done by using a potentiometer, a pot. Okay. Then you will see pin number 8. This pin is not connected to any circuit inside 741 IC. It's just a dummy lead used to fill the void space in standard 8-pin packages. Okay. Then we'll go to see some ideal characteristics of op-amp. The important ideal characteristics. Ideal means they are not practical, they are theoretical. So ideal characteristics of op-amp. So the first ideal characteristics is open loop voltage gain A. Now this open loop voltage gain A is always infinite. Ideally it is infinite. That is the open loop voltage gain without any feedback. There is no feedback, it is an open loop. So for an open loop, for an ideal op-amp, the voltage gain is infinite. Okay. Then second one is input impedance Z in. Input impedance is defined as the input voltage by the input current. The input impedance of an ideal op-amp is infinite. So input impedance, which is called as Z in, will be given as input voltage upon input current. Okay. So uh, this will be infinite. This will be infinite, very high in case of ideal op-amp. Okay. Then third we'll go to see output impedance Z out. Output impedance is defined as the ratio of output voltage to the output current. Right? So here it is output voltage to the output current. So here your Z out will be output voltage upon output current. The output impedance of an ideal op-amp is 0. So this should be ideally 0. Okay. So here it is not input current, it is output current here. So this you can make as output current. So it is a ratio of output voltage to the output current. The output impedance of an ideal op-amp is 0. Then we'll go to see what is bandwidth. An ideal op-amp has an infinite bandwidth. That is, it can amplify any signal from DC, that is zero frequency, to the highest AC frequencies without any losses. Okay. Then fifth one is offset voltage VIO. The offset voltage of an ideal op-amp is 0, so it should be 0. If it is not 0 practically, then we use the potentiometer between pin number 1 and 5 and we see that it is 0. Okay, but ideally it is 0, which means that the output voltage will be 0 if the difference between the two inputs, inverting and non-inverting terminal, is 0. Okay. Then sixth is common mode rejection ratio, CMRR. The CMRR of an ideal op-amp is infinite. That means it is able to reject all common mode signals. If the signals applied to inverting and non-inverting terminals are same, then it will reject the signals. Okay. Then we'll go to see some applications of op-amp. Op-amp can be used in many applications. So here the first application we are seeing as op-amp as an inverting amplifier. So here this one input is there which is given to the inverting input. So if this is your input here, so the inverting amplifier will give a output like this. Okay, output like this. So inverted version. Because the other terminal is grounded, then the difference will give only the one input, and that one input will be inverted at the output and amplified. So this is inverting amplifier. Similarly, you can use it as non-inverting amplifier, where the input will be given to the positive terminal here. So here you are going to use the input here, and because it is given to the non-inverting input, the output will be amplified version of the input, and there will be no phase shift here. Okay. Then you can use op-amp as an adder or a summer amplifier. So here the output V out will be equal to the sum of the input voltages. So V1 plus V2 plus V3. Okay. So the V1, V2, V3 are the input voltages. So the output will be summation of the three inputs. So it is acting as an adder or summing amplifier. Then out op-amp as a differentiator. So here if the input is the square wave, okay, so here if the input is a square wave, then output will be spikes. Okay, so here a capacitor C will be in series with the inverting input, and R will be a feedback resistor. So C and R will give you the work of differentiator. If you reverse the process, if you reverse the locations, then you can make op-amp act as an integrator. So here you can see C and R of a differentiator have interchanged the position, So here, if you give any square wave as input, the output will be a triangular wave. So this is an integrator. Okay. Then you can use op-amp as voltage to current converter. Any input voltage can be converted into a current at the output. And similarly, you can have current to voltage converter. Any input current will be converted to output voltage. Then you can have op-amp as voltage comparator. Here there are two inputs, V in and Vref. So V in and Vref will be compared with each other, and the subtraction value of that will be the output. Okay. So you can use op-amp as a voltage comparator. Okay. Thank you, students. These were some of the applications in the end we saw about op-amp. Thank you, students.